Welcome to the Inquisitive Engineer. Have you ever wondered how man got their first realistic estimate of the speed of light? It also has an interesting tie to navigation on the open seas. The speed of light has perplexed man for centuries. Well, it was easy to understand that sound had a finite speed because an event happening at some distance, we always hear the sound after we see the event happening. Many attempts were made to measure the speed of light over centuries, but the biggest problem is that our brains are just too slow to react to the events that are happening. One of the best examples was using a lantern on two mountaintops or two hilltops at say tens of miles or tens of kilometers away with a few simple instructions. If I was going to run the experiment, my instructions to the person on the other hill would be that I am going to cover my lantern with something, and when I reveal my lantern to you, the light is going to take some time to get to you, and once it gets to you and you see my lantern, you uncover your lantern, and then it is going to take some time for the light to go from your lantern back to my eyes, and I am going to be able to document how much time it took. The problem is that even by the time we see something and our brain registers it, it is at least tens of milliseconds, if not hundreds of milliseconds. And then you add in that we have to do something and remove an obstacle in front of our lantern. So at best, it's going to be several hundred milliseconds of delay in the experiment just for our brains to process what is going on. Well, at the speed of light, a beam of light going around the equator of the Earth would go around about 7.5 times in a second. So even if lanterns were hundreds of miles away on mountaintops that you could see if the curvature of the Earth didn't have an effect on it, we simply cannot process the information quick enough. This question would go unanswered until the 1600s. An important invention came along in 1608 that set things in motion to measure the speed of light. And in 1608, the telescope was invented, and it set the intellectual world by storm. Within just 2 years, Galileo had his own telescope and he pointed it towards Jupiter, and he noticed that there was 4 moons orbiting around Jupiter. This was fascinating at the time because for all of humanity, all that we could see was the things that we could see with our naked eye. And now all of a sudden we look at one of the most awe-inspiring objects in the night sky, which is Jupiter, only to find out that it also has things orbiting around it. Within 10 years of the invention of the telescope, Kepler came up with his 3 laws of planetary motion. It's probably difficult for us to fathom just how amazing and awe-inspiring a telescope was when you turned it to the heavens in the 1600s. And as such, many people did so, and the moons around Jupiter were a rather fascinating observation, such that the point where many different people figured out the orbital times for all of the moons. And in particular, the moon that orbits closest to Jupiter, which is Io, orbits Jupiter in about 42.5 hours. If you know the orbital period of a particular moon around Jupiter, you can predict when future orbits are complete. You can predict when the next one's complete, the 10th orbit from now, the 100th orbit from now, and even the 1,000th orbit from now. So you can go ahead and write these down in a book and make predictions on when these events are going to happen. Now, this became of particular interest for navigational purposes on the open seas because one of the greatest problems of the time was knowing what longitude you were out at open sea or where you are around the globe. These predictions that are written down in the book could be given to a ship's captain, and a ship's captain at night on a particular day could go to that book and see what time that event is supposed to happen, and he can go ahead and see how far off he is from that event, and from there he can predict just roughly where he is longitudinally around the Earth. Now, this proved to be rather impractical because ships on open seas aren't exactly very steady, and it became very difficult to actually see the moons of Jupiter as the ship is moving up and down. But there are some curious observations that came out of preparing these books. Between 1666 and 1668, Cassini was observing the orbit of Io around Jupiter, and what he noticed was that there was a spread of about 20 minutes between the two worst predictions. What he noticed were some of the observations were ahead of the predicted time, and some observations were behind the predicted time, with the span of the furthest ahead of predicted time to the furthest behind predicted time being about 20 minutes. Now, Cassini seemed to have abandoned this study, but it caught the attention of Roma. And Roma was so inspired by it that between 1671 and 1677, he took his own detailed observations of Jupiter and came to the exact same conclusions that Cassini did. And he came up with that the events were a spread of about 22 minutes between the one that was the furthest ahead of prediction and the one that was furthest behind prediction. So what events were Cassini, Roma, and others looking at? Well, they were actually looking at the eclipse of Io behind Jupiter. Let's go to my whiteboard to understand that a little bit better. So what Cassini, Roma, and others were looking at was the eclipsing of Io by Jupiter. So what do they mean by the eclipsing of Io by Jupiter? Well, the sun casts light out towards Jupiter, and because Jupiter is a very great distance from the sun, and the sun is the only source of light in the solar system, Jupiter actually casts a shadow behind it. And now, if we assume that this penny is Io, as it orbits around Jupiter, it eventually falls into the shadow behind Jupiter, and then also reappears from the shadow behind Jupiter. Now, depending on which side of the sun the Earth is on, depends on how we can see if it goes into the shadow or out of the shadow. So if Earth is on this side of the sun, our line of sight towards Jupiter this way, and as Io goes around, we can obviously see it go into the shadow behind Jupiter, but we can't see it clear the shadow behind Jupiter because we could only see about that far. Likewise, if Earth is on the other side of the sun, the line of sight is that way, and from Earth we can't see Io actually going into the shadow of Jupiter, but we can see it coming out of the shadow of Jupiter. Now, Roma did not publish his data, but he did lecture on his data. And that drew the attention of Huygens, and Huygens worked with Roma to use his data and come up with a calculation for the speed of light. Now, modern measurements did not exist in that time. The meter didn't come around until late 1700s, really about 1800. So what he used was the French measurement of the toise. And if we estimate what the value of the toise was that he used, we can back estimate to get an idea of just how close they were to modern values for the speed of light. And different sources say that that was somewhere between 70 to 75% of the modern day accepted value for the speed of light. Now, this was based on the 22 minutes from the worst case of Roma's data and what the estimate of the distance from the Earth to the Sun was at the time. Now, by far the biggest error in this calculation was the 22 minutes between the two worst observations when the Sun is in between Earth and Jupiter and when the Earth is between the Sun and Jupiter. So these two events happen 6 months apart. In modern day, known values for that span of 22 minutes is closer to about 16.7 minutes. So Roma was a little bit more than 5 minutes off. Now that doesn't seem like much, but this is 5 minutes over a 6-month time period because the Earth has to travel halfway around the Sun. We give credit today that clocks are super accurate. Even your wristwatch today is way more accurate than clocks were back in the 1600s. Prior to 1660, clocks were very, very inaccurate, losing potentially 15 minutes a day. And around 1660, pendulum clocks really started hitting the scene, and they were about 10 or 15 seconds inaccurate per day. Now, that may not seem like a lot, but over 182 or 183 days or 6 months, that adds up to anywhere between 30 and 45 minutes of time that the clock either got ahead or behind real time. So how did Roma get within just 5 minutes of the current value? Well, realistically, they would reset their clocks to the solar day. And the solar day is when the sun is highest overhead, making the longest shadow of the day. This could easily be measured by a sundial or a stick, and you could reset your clock every day to that high noon. Now, a solar day is not exactly 24 hours. It varies throughout the year. Sometimes it is up to 16 to 17 minutes ahead or behind the actual time. Now, why is that? Let's go to the whiteboard and see why that is. What Kepler noticed was that planets do not revolve around the sun in perfectly circular orbits. They are slightly elliptical. This is exaggerated to a large extent, but an elliptical orbit would be something like this, where the planet at some point is further from the sun on one side than it is from the other. Now, because of the effect of gravity, a planet travels a slower speed over here than it does over here. So in the same amount of time, let's say the sun is there and the Earth is pointing towards the sun, and that is your degree of longitude, and this would be high noon at that longitude. Because the Earth is moving slower on this side of the sun compared to that side of the sun, when it takes 24 hours or a day to rotate, it hasn't moved quite as far. So to get your longitude back to high noon, it's got to rotate just a little bit more than 360 degrees. However, if it is on this side of the sun and we're at high noon, in 24 hours, as it rotates, it's going to travel a greater distance. And now, for your longitude to be pointing back at the sun to be high noon, it's got to rotate even more than it would have as if it went from here to here. And so while the Earth is closer to the sun, from high noon to high noon is longer than it is from high noon to high noon out here when the Earth is at greater distance. Now, Roma would have more than likely adjusted for this different length in the solar day, but I am unsure just how accurate they knew that changed from day to day over the course of the year. So it is rather impressive that they were only about 5 minutes off. Fast forward about a century and a half, and technological advancements in telescopes and equipment to measure extremely minute changes to geometric angles, and also much more accurate pendulum clocks where you could easily track time across the 6-month period down to probably just a few seconds. With all those technological advancements available and decades of very detailed observations of heavenly objects, in 1809, French astronomer Delambre calculated that the time it took light to go from the sun to the earth was about 8 minutes and 12 seconds. Now, Delambre did not give an exact velocity for the speed of light, but if we use the modern day values for the distance from the sun to the earth, we can go ahead and backtrack and recalculate the speed of light that he would have came up with, and that value would have been just over 300,000 kilometers per second. That is pretty darn close to the modern accepted value of just under 300,000 kilometers per second. So he was realistically within 1 to maybe 3% of the modern day accepted value. That's pretty impressive by just watching heavenly objects. The next improvement in further refining the speed of light involved precision machined parts and observations in a laboratory, but that is a discussion for another video. If you like this video, please like and subscribe. Feel free to leave comments, and as always, stay curious.